Okay, so in the comments of one of my previous videos, there were a few people asking how my physics-based flight modeling works. So I'm going to do a high-level overview. In its basic form, this is actually a very simplified version of blade element theory as you know it from like X-plane or DCS world. This is of course much simplified for more arcadey type of simulator. I'm only sampling one point on each airfoil, or in case of wing 2. I'm using Unreal Engine's built-in socket system to determine a point at which the sampling is done. As you can see, the points are located on various points of wing, tail, and I also have one on the propeller, but I'm not using it at the moment. Okay, so at each point, hold on a sec, on each point I'm calculating forces acting on the airfoil and then just using Unreal Engine's built-in physics to integrate those forces. And here's the blueprint. It's a bit of a clusterfuck, but I'll try to explain what it does step by step. So first of all, you have this function that determines location of the socket and its rotation. From this, I sent these coordinates to this function, which is get physics linear velocity at point. This calculates linear velocity, but also takes into account rotation of the object. So in case the object is rotating, in case of our simulator the airplane is turning, the velocities on different parts of the aircraft will differ. In case of, for example, a turn, the velocity of outer wing will be higher than velocity of inner wing, which means more drag, which means the airplane will have will resist the rotation. In other words, it will be self-stabilizing, just like a real airplane. Okay, so from this, in addition to this velocity, I also calculate the forward vector, up vector, and right vector of the socket. The reason for doing this is that the airplane doesn't always fly straight on level, and of course some of the surfaces like rudder are mounted in a different orientation than the rest of the aircraft. Same actually goes for main wing, which as you can see is slightly tilted to cause dihedral effect, which helps to control or to reduce roll inertia, making the aircraft more stable. Okay, so after calculating these three vectors, I'm moving on to next part of the blueprint, which actually calculates velocity related to air. Now, in my simulation there is no wind. However, I do have air pressure changing with altitude. This is a very simplified function, just assuming a linear decrease of air pressure with altitude. This is valid up until 15,000 feet. As you can see in this particular example, I'm just using simple GA aircraft, which isn't likely to go any higher, so fuck it. Here I'm dividing the velocity by 100. This is because Unreal Engine, a single Unreal Engine unit is 1 centimeter or 1/100th of a meter. However, the mathematical formulas I found were in meters and newtons and so on, so I divided by 100. Next, I calculate dot product of these vectors I talked about earlier, forward vector and so on, with this velocity. And this will give me separate forward, up, and right velocity. In other words, forward velocity is the velocity that would be measured by a pitot tube. Right velocity would be your slip, and another calculation will calculate the alpha. I'll get to that in a second. And one more thing I'm calculating is the stream. This is a bit hard to explain, but airfoil calculation doesn't take into account actual slip. It only uses airstream and alpha, which is difference between zero lift line of the airfoil and the actual direction of the airstream, which is simple, simply multiplying the forward vector and up vector with respective velocities, and then just adding them up. Okay, and the length of this vector is a stream velocity, and I also calculate by rotating this stream direction by minus 90 degrees along the right vector. This calculates a vector that's 90 degrees off the airstream. This is the direction in which lift will be applied. Moving on, and this is the meat of the airfoil calculation. And excuse me, this is a bit of a spider's nest, because, well, it's kind of complicated formula. So I broke it down into multiple forces that are acting on the airfoil. You can see there's lift and two forms of drag, which is induced, a side effect of wing vortices, and the form drag and the skin friction and deflection drag are combined into one. And of course, finally, I'll just add these three up, apply them on the location of the socket, and that's basically it. As you can see, I also apply force to a bone to which the socket belongs, which will allow me to later create aircraft with varying geometry. Not used at the moment, but the possibility is here. Okay, I probably gonna have to go to more detail on individual parts, so might as well do it. This is the simplest part. This is the control surface deflection, and I can actually explain that I'm using float curves to control how these forces vary based on the angle of attack So I have, in this model, I have three curves, which is lift curve. As you can see here, if the airplane is flying straight at zero angle of attack, the lift is zero. If you pull up, the lift will increase until you reach point in which it stalls. Then you have some residual lift. If you're falling straight down, lift is zero, and there's a bit of lift if the airplane is flying backwards, but of course the airfoil is not effective that way, so lift is diminished. There's also another part of the curve. If the angle of attack is negative, in other words, if you push down hard, the wing will actually generate negative lift. Again, diminished lift if flying backwards. Next we have drag, or actually just one component of the drag. This is form drag, which varies with the angle of attack. As you can see, if the plane is at zero angle of attack, it's, well, zero, and it increases up until 90 degrees, at which point basically this is the point in which the airplane is falling straight down and air resistance is massive. And again, as it is approaching flying completely backwards, it once again decreases. Actually, in real world it would be higher at this part of the curve, but I don't have actual numbers. All the lift drag curves I could find only dealt with forward flight, so this is just guesswork. And finally we have curve that controls the effectiveness of control surface, in other words, ailerons, flaps, and so on. As you can see, in normal straight and level flight they are fully effective, and as you approach stall, the effectiveness will diminish, and once again at 90 degrees the control surface will be completely ineffective because of no airflow. Again, if your aircraft would somehow, I don't know how, got to fly backwards, the control surfaces would actually act in reverse. Okay, so back into our actual blueprint. Here it is. So I get the float value of selected curve. In this case, this is the control surface effectiveness. I'm gonna multiply it by how much currently the control surface is deflected, and of course add it to the lift. This is the extraction of the value of the lift curve, and added control surface. This whole thing is multiplied by square of the current true airspeed, which is basically just your Unreal Engine's speed. Maybe you could in previous phase add current wind or something, multiplied by current air pressure. What's this? I actually forgot what this is. Oh, this is the air density, this is the velocity. Okay, so sorry, small correction. That third multiplication is actually area of this section of the airfoil. Sorry, I forgot to mention it, and actually you helped me find a bug because I forgot to multiply the induced drag by the area. And now finally I had to multiply this number, this result, by 5. Now, this is because of one quirk of the Unreal Engine. 1 unit of force, if you use blueprint apply force node, is 0.1 Newton. Okay, the actual formula will give you results in newtons, but you're in the formula you're supposed to divide it by 2. So I just collapsed this 2 into one node. This is then multiplied by this upward component of the airstream, and that's your resulting lift. Now, induced drag is a bit complicated. I don't know if I can properly explain it. Maybe later. Just copy it as it is. This is the formula I found on the NASA website. Hopefully they know what they're doing. So, and actually, just a little warning. They say this formula breaks down when the aircraft is in deep stall, so it's not 100% accurate, but I don't have any more accurate calculation. In a nutshell, it uses square of the coefficient of lift, again multiplied by airspeed, multiplied by air density, and now this whole result is divided by pi times aspect ratio of the wing. In other words, basically a glider with a long thin wing would have less induced drag than let's say a Delta fighter, right? And this is once again multiplied by efficiency of the wing, which is actually very hard to calculate, but generally elliptical wings, like some you would find on say a glider or Supermarine Spitfire, have 100% efficiency, or the number would be 1 or close to 1. Your typical square wing has around 0.7, and this whole thing is used to divide results of the previous calculation, again multiplied by -5, because of course drag is acting in the opposite direction of the airstream. Again, add up. And finally we have deflection drag. This is a very simplified calculation. I just took the deflection of the control surface and added it. Next we have skin friction, which again actual calculations would be too complicated for a video game. Even for a serious simulator, I don't think even X-Plane calculates it properly. So I just added some simple fixed number that's approximation of skin friction that you would find on a modern airplane. If you were simulating like something like a World War I biplanes or something along those lines, this number would be higher. And finally we have form drag, which is this curve. This actually varies with angle of attack, as I explained earlier. Again, multiply by air density, multiply by square of the airspeed, multiply by -5. This whole thing is added, and well, that's basically it. That's your airfoil calculation. Now, in this particular simulator, I do not take into account drag of the fuselage, but that's fairly simple, and actually Unreal's built-in linear damping should approximate it well enough. Okay, that's pretty much it. If you didn't understand some of the parts or something, maybe I can do a better explanation. Oh, and finally, one thing that I forgot to mention: ground effect. Now, if your airplane is flying very close to the ground, about half of the length of the wing, it will disrupt production of the wingtip vortices, which will reduce induced drag. This could be simulated by doing a ray cast from the tip of the wing towards the ground. However, I'm not doing it at the moment, maybe later, because I haven't found exact relation between altitude above ground and how much is the induced drag reduced. So, homework. Just a final note, because this model applies forces on different parts of the aircraft, the actual location of the sockets is fairly important. In order for your aircraft to fly realistically, the socket should be located about 1/4 of the way from the leading edge to the trailing edge. This is known as center of lift. In reality, this location shifts with increasing velocity, but this is only relevant at speeds approaching Mach 1. So for general aviation aircraft, fixed location is good enough. Same goes for tail, again around 1/4 of the way. And same goes for vertical stabilizer, and also its location from in the lateral axis is also fairly important, especially for the part of the wing where aileron is located. The further away from the center it is, the more effective the aileron will be. And here's another small quirk of the Unreal Engine, is that it assumes that the mass of the physical object is uniformly distributed. In other words, the wings of the airplane will be fairly heavy compared to real world, if your overall weight of the aircraft is realistic. So it would be, if you make an exact replica of the real aircraft, it will be slightly lazy in the roll axis compared to the real one. So as a compensation, you may want to move the socket of the part of the wing that contains aileron a bit more towards the end.